When developers begin searching for a green hydrogen project location, one question often dominates the early discussion. Where are the best renewable resources? Where is the strongest solar irradiation? Where is the best wind? Where can we generate the lowest cost renewable electricity? Those are important questions, but they are not enough because the location with the best renewable resource may not be the location where the best hydrogen project can actually be built. In this video, we are going to look beyond the resource map and examine hydrogen development as a complete system. And by the end, we will see why finding the best hydrogen site requires understanding not just resources, but infrastructure, water, land, markets, technology, permitting, economics, and the relationships connecting all of them. Imagine we have identified a candidate location. The map looks almost perfect. The solar overlay is strong. The wind overlay is promising. There appears to be large areas of open land. From a desktop screening exercise, the site immediately rises to the top, and this is where many projects begin. Before anyone has walked the ground, before infrastructure has been investigated, and before the wider project system has been studied, the map already seems to be saying yes. But a renewable resource map shows only one part of the project. The real question is what happens when we begin adding the other layers. The first layer certainly looks encouraging. Solar resource is excellent. There is high annual irradiation, a relatively stable seasonal profile, and a large area potentially available for solar generation. At first glance, those conditions appear ideal for producing low-cost renewable electricity. And because electricity is a major input into electrolysis, this can make the site look extremely attractive for hydrogen production. But notice the qualification on this slide. These values are illustrative. We are not trying to prove that a particular project works. We are illustrating a much more important principle. Strong solar resource is useful information, but it is not yet a project development decision. Now the candidate becomes even more attractive. It also has strong wind. Good wind speeds and a favorable hub height profile could provide another renewable generation source. And when solar and wind generation profiles complement each other, the combined generation profile may become more useful to a hydrogen project. Solar may dominate during daylight hours. Wind generation may follow a different pattern. That combination can improve how renewable generation aligns with electrolyzer operation. At this stage, the project can begin to look almost irresistible. Excellent solar, strong wind, large land area. Surely this must be a great hydrogen location. But this is where the dangerous assumption begins. The assumption seems logical. If we have abundant renewable energy and potentially low electricity costs, then surely we should be able to produce cheap hydrogen. Electricity is central to electrolysis, so lowering electricity costs certainly matters. But hydrogen projects do not end at the electrical connection to an electrolyzer. There is an entire physical and commercial system surrounding that machine. The hydrogen has to be produced, compressed, stored, transported, sold, and delivered. The project needs land, water, infrastructure, approvals, technology, capital, and customers. So cheap electricity may create a powerful advantage. But cheap electricity alone does not guarantee cheap hydrogen. And it definitely does not guarantee a viable project. Now we zoom out. The candidate site may have great renewable resources, but perhaps there is no transmission infrastructure, no hydrogen pipeline, no customer, no reliable water source, and perhaps not even adequate road access. Suddenly, the perfect location starts to look very different. This is the central reveal. A renewable resource map can tell us where energy exists. It does not automatically tell us whether a complete industrial hydrogen system can be built around that resource. A project can therefore look extraordinary when viewed through one layer and become extremely difficult once the missing infrastructure is revealed. This is the reframing that changes everything. An electrolyzer is a machine. A hydrogen project is everything that the electrolyzer depends on. Look at the diagram. Renewables, the grid, and water feed the electrolyzer. On the other side, hydrogen must move into storage, transport, and ultimately to an offtaker. And the entire system must be capable of attracting finance. So instead of asking whether the electrolyzer can operate at the site, we need to ask whether the complete system surrounding that electrolyzer can function. This is why hydrogen project development is fundamentally a systems problem. Every major component depends on something else, and weakness in one part of the system can undermine everything around it. Renewable resource remains essential. Nothing in this argument suggests otherwise. Generation profile, capacity factor, and curtailment risk all matter. But renewable resource is the first layer, not the final answer. A great resource can support a strong project, but it cannot compensate indefinitely for missing infrastructure, an absent market, difficult permitting, or impossible logistics. So the question changes. Instead of asking, where is the best renewable resource? We ask, how strong is the renewable resource when viewed as one component inside the complete project? That distinction is critical. Resource quality and project viability are related, but they are not the same thing. Now we add electricity infrastructure. A remote site may have excellent solar or wind, but how far is it from the transmission system? Is a suitable substation nearby? What does interconnection look like? Is grid capacity actually available? These are not minor details. Distance to the electrical system can translate directly into additional capital expenditure. New transmission lines, substations, interconnection equipment, and grid upgrades may be required. And as the slide emphasizes, a remote site can require enormous transmission investment. So renewable electricity that appears cheap at the generation source may become far more expensive once the supporting infrastructure needed to deliver and manage that electricity is included. Then comes water. Electrolysis requires a dependable water supply, but the analysis cannot stop at identifying a blue area on a map. We need to understand the source. How will that water be treated? How will it reach the project? What happens to discharge streams? What will the water cost? And what permits are required? Depending on the site, options may include freshwater, desalination, or wastewater reuse. Each option creates a different infrastructure configuration. So the water layer is not simply about whether water exists, it is about whether a reliable, permitted, technically suitable water system can support the project over its operating life. Next is land and terrain. A very large site is not automatically a good site. Flat, dry, accessible land can be much more useful than a larger area with difficult terrain. Why? Because terrain affects earthworks, foundations, roads, drainage, equipment access, and construction schedules. Ground conditions can change foundation requirements. Flood exposure may introduce additional design constraints, and land availability is different from land tenure. Even if land appears empty, developers still need to understand who owns it, how it can be accessed, and what rights are required. So this layer turns the project from a map location into a physical construction site. Then we encounter another category of information that may not appear clearly on the renewable resource map: environmental constraints. Some areas simply may not be available for development. Protected land, sensitive habitat, biodiversity concerns, and environmental permitting requirements can significantly reduce the amount of usable land. This means a site can appear large geographically while the actual developable area is much smaller, and this is why exclusion zones matter early. Developers do not want to discover late in development that the portion of land they assumed was available is restricted or requires a fundamentally different project design. The resource map may say yes, the permitting process may say something very different. Now the hydrogen itself enters the infrastructure problem. Producing hydrogen is only the beginning. Once hydrogen leaves the electrolyzer, it may need compression, it may need storage. It may need pipeline infrastructure, loading facilities, terminals, or other delivery systems. And those systems must operate according to a schedule. The project is therefore not simply a hydrogen production facility, it is also a hydrogen handling and delivery system. If the hydrogen cannot be stored or moved economically to where it is needed, then a low-cost production site can lose its advantage very quickly. The molecule has to reach the customer. That requirement changes site selection. And now we reach one of the most important questions in the entire project: who buys the hydrogen? The potential customers shown here include steel, ammonia, refining, heavy industry, ports, and export markets. But regardless of sector, the underlying principle is the same. Demand anchors the project. A hydrogen facility is not valuable simply because it can produce hydrogen. There has to be a credible market for the output. And the characteristics of that buyer matter. Where is the buyer located? How much hydrogen is required? What delivery profile is expected? What specifications must be met? Without a buyer, even extraordinary renewable resource quality cannot create a commercial project by itself. Once the buyer is identified, distance becomes economics. How far is the hydrogen plant from the market? Can hydrogen move through a pipeline? Does delivery require trucks or rail? Is a port involved? Every additional logistics requirement introduces cost, infrastructure, operational complexity, and risk. This is why two sites with similar renewable resources can have dramatically different project outcomes. One may be close to the customer, the other may require major new transport infrastructure. So geography needs to be measured not only in terms of sunlight and wind, it also needs to be measured in terms of distance between production and demand. Then every project layer encounters a gatekeeper. Land use may require one approval, environmental review another, water rights another. Grid connection has its own process. Construction requires further approvals, and hydrogen safety introduces additional requirements. These approvals often run in parallel with different authorities and different timelines. That creates another type of project dependency, time. A technically attractive project can still become difficult if one critical permission takes substantially longer than the rest of the development schedule. This is why permitting should not be treated as paperwork that happens after engineering. It is part of project architecture from the beginning. Technology must also fit the site. The project is not simply about selecting an electrolyzer model and installing it. Electrolyzer sizing depends on the energy supply and the required hydrogen output. The project may need batteries or other buffering strategies. Storage may be required to manage the difference between variable production and contractual delivery, and the operating strategy needs to reflect the actual resource profile. This creates another important relationship. The site affects the technology configuration, and the technology configuration affects project economics. So there is no universal hydrogen plant design that can simply be dropped onto every promising renewable location. Eventually, all of these layers converge in economics. The slide shows a simplified levelized cost of hydrogen stack. Electricity matters, but so do the electrolyzer, water, storage, transport, infrastructure, and finance. The proportions on this slide are illustrative rather than a real project estimate, but the principle is essential. Every layer can change LCOH. This is why focusing only on low-cost renewable electricity can be misleading. A site may save money on generation and then lose that advantage through transmission, water infrastructure, transportation, storage, or financing requirements. The economic outcome is produced by the complete system, not one variable. Now the key insight becomes visible. Nothing operates independently. Look at the examples. The water source can affect electricity demand. Distance to the offtaker can affect pipeline cost. Renewable variability can affect electrolyzer utilization. Terrain can affect construction cost. Grid access can affect operating strategy. Storage can affect delivery reliability. And these are only 6 examples. A real project may contain hundreds of these dependencies. This means changing one assumption can cause effects elsewhere in the system. So a hydrogen project should not be thought of as a checklist of isolated variables. It is a network of relationships. That idea takes us to the next step. Consider 3 candidate sites. Site A has the highest solar score, 95, but there is no grid for 180 kilometers and no water source. Site B has a lower solar score of 87, but it has grid and water on site and a buyer only 40 kilometers away. Site C has a solar score of 81, but it faces protected land constraints and lacks port access. These examples are illustrative, but they reveal the ranking trap. If we rank only renewable resource quality, Site A wins. If we rank the complete project system, the answer changes. The highest resource score is not necessarily the highest ranked project. Now we redraw the 11 layers. Instead of treating them as separate categories, we connect them. Renewables, grid, water, land, permitting, electrolyzer, storage, transport, offtaker, technology, economics, finance. What we are creating is no longer simply a layered checklist. It is a connected network. Each part affects other parts of the project. And this creates a more useful way of thinking about hydrogen development: nodes, relationships, dependencies, constraints, and evidence. This is the transition from conventional screening toward what we can call graph-based project thinking. This is the core methodology, the hydrogen project graph. The main project pathway begins with renewables. Energy moves through the power system to the electrolyzer. Hydrogen then moves through compression, storage, transport, and ultimately to the offtaker. The offtaker creates revenue. Revenue supports financing. But underneath that pathway are the conditions that determine whether it can actually function: water, land, permitting, infrastructure, technology, market, and risk. Every node carries constraints and evidence. Every connection carries a consequence. If one node changes, neighboring decisions may also change. The goal is therefore not just to collect project data. The goal is to understand how that data is connected. Once we understand the system as a network, scoring also changes. Instead of scoring only renewable resource quality, we score several dimensions together: resource, infrastructure, water, market. Permitting, technology, economics, risk. The radar chart shows how 3 candidate sites can have very different shapes, even if they initially looked attractive for similar reasons. This creates a more useful question. Which project has the strongest overall ability to survive technical, commercial, regulatory, and infrastructure constraints? That is what project survivability means here. We are no longer searching for a perfect individual variable, we are searching for the strongest complete system. Now compare the 3 candidates as whole systems. Site A has excellent renewable resources but weak infrastructure. It is constrained. Site C has moderate renewable resources and excellent logistics, but its overall system still has weaknesses. Site B has good renewable resources, strong infrastructure, and a nearby buyer. And in this illustrative comparison, Site B becomes the strongest overall project. That is the central lesson of the entire video. The site with the best individual renewable resource does not necessarily produce the best project. Sometimes the second best resource can create the strongest project because the complete system works better. And that brings us back to where we started. Hydrogen development is systems engineering. Finding strong solar or wind resources is important. But project development requires us to connect resource, infrastructure, water, market, technology, permitting, economics, and money. The goal is not simply to find the place where hydrogen could theoretically be produced. The goal is to find the place where the complete project has the strongest chance of working. And that is the type of connected project evaluation that platforms such as H2 Hub are being built to support. So when you look at the next renewable energy map, remember this. Don't find the best resource, find the best project.